So hi everyone. So today we'll be discussing about how do we productionize a Spark ML based application. So before we start, so how many of you here are using Spark in your day-to-day activities? So how many are in like 1.6 and who are in the latest versions? How many of you are using the RDD API still? Okay. So, and in terms of machine learning, how many are you moved to Spark ML versus MLlib? MLlib, who are lives? Okay. So Spark ML. Okay. So yeah, so this is about the stories from the Spark battlefield. Like once we start using the Spark ML in one of our application, and when we deploy and when we try to solve different problems using Spark ML, so what are the issues we started facing, and what are the kind of best practices we have to follow in terms of avoiding issues and other things. So that's what this session will be about. So we'll go into different topics and we'll be discussing about what are the best practices and what are the pitfalls we have to avoid in order to kind of have a better performant system. So let's start. So this is my introduction. So myself, Shashank, so I work for Telias and also a part-time at datamantra. So if you want to contact or know more about me, you can just go to the website and can connect. So in terms of the ML, so we'll start with the different stages of ML. In terms of stages of ML, so the first we'll normally we kind of gather the data. So here the data collection is one of the main important stages of ML. So where we collect the data from different sources, and data can be of different formats. So you use different APIs and stuff to gather the data. And the next step would be the data preparation. So what is the data and is there any schema associated with it, or after which you kind of do the cleanup, missing values, all those stuff, and then you choose a model. So based on your problem, what is the problem you are trying to solve, you choose a model to kind of solve your problem, and then we do the training. So that is what running at scale or actual machine learning training. And then we do the evaluation whether the trained model is a good model or you want to kind of tune the parameters and stuff. And then the operationalize. So many people may not worry about the operationalize piece. So your operationalize means how do you like store the model, how do you use the model for prediction and stuff. So the points which are marked as red is what we'll be concentrating about. So those are the areas, key areas where we'll be pointing out few issues, what we found, and the solution to those issues. So the motivation behind this talk was Spark ML is a end-to-end solution. So you can do from data cleanup to kind of training, evaluation, and prediction, everything. So you have the support for doing all of these things. So whereas in terms of MLlib, so we didn't have the data cleanup activity and didn't have like a pipeline support and other stuff. So here we have everything, but even with that, so we have few missing features and also few issues in terms of the best practices and other stuff. So what are the few things is custom data preparation techniques may be needed. Like not everything is like currently provided by Spark. You just use them and kind of solve your problem. So we may need some custom preparation techniques. So one is in terms of general techniques, and also for a specific type of data or a specific type of problem. So you may have to kind of do some custom techniques. And also efficient resource utilization. So in terms of when you are working at scale, so when you are handling like terabytes of data, so you have to use the resources efficiently. So you cannot just keep all the data in memory to just speed up, because so there is like a cost associated with it in terms of big data. Even another copy of the data will cost you like another big chunk of RAM for you. And in terms of operationalizing, so after you train the model, so how do you use that? So here it's not just like we train the model and we just got to know that the model is the best model and we don't use it. So we need to store it, we need to use it for prediction, and after we store the model, so what are the different ways we kind of go with. and what are the best practices. So that will be the motivation towards the talk, and we'll be discussing about each of these in detail. So first we'll talk about the introduction to Spark ML. So this introduction is not like a full complete introduction to Spark ML. So we just touch upon pieces what we will be using in our talk. So if you are interested to know more about Spark ML and different things, so we already have done a meetup in before, like few months ago. So you can just go through the YouTube video and you'll be able to find that. So in terms of Spark ML, it provides a higher level API for like construction and tuning of ML workflows. So basically, it is built on top of the data frame or the data set of Spark. So all of your machine learning algorithms or the data cleanup techniques so work on top of data set. So there are few abstractions here. So there is something called a transformer, estimator, evaluator, and a pipeline. So here we will be using a transformer estimator pipeline. So we will not be touching about the evaluator piece. So what is a estimator? What is a transformer? A transformer is a basic as an abstraction in Spark ML, where it can be abstracted as a transformation which takes a data frame, does some transformation, and returns you back a data frame. So it can do any type of task like adding a column or cleaning up a column or doing any kind of work, but basically it takes a data frame and it returns a data frame. So normally this transformer is used in the logic where you are doing some kind of logic like on a per row basis. So you take a row of data, you do some transformation, and then you write the row to a so the logic is it takes a data frame and it gives out a data frame. So that's what a transform. So one of our example is a vector assembler. So there is a transformer built into Spark called the vector assembler. So what it basically does is it takes all the different features, different columns which are to be treated as features in your machine learning algorithm, and it combines them into a single column which is of type vector. So it just converts those individual columns which has the feature values into a vector. That's called vector assembler. So here we are talking about a row to row operation. So you take a row, take different values of different columns, and you kind of create a vector out of it. So that's what vector assembler is. This is one of the example of a transformer.
One question is, so when it assembles, when it transforms into a vector, does it utilize more space?
Which one? Yeah, because it's adding a new column, right?
So there will be more space than existing data frame?
Yes, yeah. So next is in terms of estimator. The next one is an estimator. So estimator can be the abstraction of estimator is kind of a algorithm training piece. So where you will fit the model first using a data, and which will return a model, and a model will again be a transformer. So you can assume it as some kind of like a linear regression. It takes a data, it fits a model, it will return back a linear regression model, and which is a transformer. So which can take a data and transform the data, and which can add like a predicted label or something, predicted column. So that's what estimator is. So estimator has two steps to it. One is it should fit the model, and then the model is a transformer, so which will be which will support taking a data frame, transforming it to another data frame. So another example for estimator is a string indexer. So where if you have a categorical column, so normally how do you use it in a machine learning algorithm as a feature? So we kind of index those values. So those unique values will be converted into indexes, and that will be used as a feature, because machine learning is all about mathematics and it expects the values to be numerical. So you convert these string values to numerical, and that is done by string indexer. It takes the unique value of a specific column and creates indexes. So that's what it did. So salary is the column which was taken as an input, and it
string indexer is for category variable.
Yes. So it takes the unique values of the a specific column, and it will index the values and adds a new column. So basically what happens in the fit step is, so it kind of finds the unique set of values in the data set. So it stores it in the model, and when you do a transformation on the model, so that is when it adds a column, because getting a list of unique values is not a row level operation. So you will have to do it in the fit step, and in the transform step, adding a new column is a row level step. So it will be done in the transform stage. So that is what one of the example for estimator. So next is a pipeline. So pipeline can be assumed as a chain of a transformers and an estimator. A pipeline itself is an estimator. So where you create a pipeline which can contain different transformers and different estimators. So when you call fit on a pipeline, because pipeline is an estimator, when you call fit on the pipeline, so it kind of calls fit on all the inner stages of the pipeline, and the model what you get is called a pipeline model. So the pipeline model what you get will have all the transformers in it, and when you say pipeline dot model dot transform, so the data goes through all the different stages. So there can be like stages like a string indexer, a vector assembler, and many different stages chained together, and also an algorithm and also a predictor. So everything will be there. So once you do a model dot transform, it can do that on the prediction data set at once. So that's what about the pipeline. So this is about the existing features. So so we will be using that in our code as well. So we didn't discuss much about like how to use it in the code. Because
What version of Spark is this?
sorry,
The version of Spark you are telling all this.
it's 2.2.0. So the one we are using is 2.2.0. It's there from 1.6. So now we'll talk about like what is missing. So what is the missing link between these things? So one is in terms of data cleanup. So there are few features which Spark does not support built-in terms of data cleanup. So those are the few features which we'll be discussing. One is regarding the null values. So people who have used machine learning or who use machine learning know like how it cannot handle null values. So null values is basically missing values. So missing values can occur in a data set because of many reasons. The only way to kind of use it in a machine learning is you need to handle it in some way. So handling it can depend on the type of the problem or type of the column or how many nulls are there, like what is the percentage of null values in that specific column. There can be like a different steps. So basically nulls, and also Spark ML doesn't handle nulls gracefully. So whenever it finds a null, it just throws a runtime exception that it found a null. So then it's hard to kind of debug and other things. So it's always recommended to use a null handler before using any of the Sparks.
In such a case, then why should I go for Spark ML? Because naturally I have handled a lot of data where the null values were there. You are telling that Spark ML doesn't handle null values.
That's what I'll be talking about, how we can handle null values.
Okay.
So Spark. So how do you do that? So normally we have support for building our own custom pipeline stage in Spark ML, so which we can use to kind of to handle nulls. And so basically, like what technique should be used to handle nulls will completely depend on the domain expertise. So, but we will build a basic null handler stage, so which is capable of handling a few type of ways of handling the null. So, what do you need for building a custom Spark ML stage? So first we'll start with a transformer. So handling nulls should be a part of the pipeline. So we can kind of keep the handling null code separate, and we can just get our data, go through that, and then send our data to the Spark ML pipeline. But that's not like a right way to do it. The best practice is to build the custom pipeline stage, so that will be also a part of the pipeline, and you kind of have the data go through the complete pipeline. So we have a few APIs to build our custom transformer. So here we will be building a custom transformer. So basically there are two methods which we need to override in terms of implementing a custom transformer. One is a transform method and another is a transform schema method. So what is a transform method? A transform method is a similar method we discussed about the transform. It takes a data frame and it does some modification, and then it will return a data frame. So transform schema is basically used for validation of the schema. If your code is expecting the input column to be of a specific type, then you check all those things in transform schema. So whenever a Spark pipeline is ran, fit or transformed, so it always calls the transform schema first, then based on the success of the transform schema method, then only it goes to the transform method. So basically it calls transform schema on the complete set of your stages. So you need not wait for a long time to get an error that the schema mismatch is present. So it goes through the transform schema on all of your pipeline stages. So that's what it does. So basically you need to implement these two things. So we'll go to the code now. So we'll see the code null handler transformer. Yeah. So this is the null handler transformer we have. So if you see, we are extending a transformer abstract class, and we are implementing a few methods. So I will talk about the input call. So this is the transform method we have. If you see, it takes a data set and returns a data frame. So data set and data frame are kind of similar. So we'll not get into like what is the difference and why the API is such that. So we get a data set, and we return a data frame. So we take the input column on which we want to kind of handle the null, because we need to know like on which column we need to handle the null. So we take that input column, and there is another configuration called how do you want to handle it. So it's called handle with. So we'll get that configuration. So basically these configurations will be set by the user of this API. So we'll match whether it's a 0. If it is a 0, so basically what we are doing is that, so dataset.na functions are utility functions on a data frame. So where you can handle nulls, or you can fill the missing values with a specific value. So that's what we are doing. We say dataset.na.fill with 0, and in the second parameter we are giving a list of column names. Next is
the different options, like filling with 0, or when it is numeric, what are the options?
Sorry? Options.
When it is a numeric variable, what are the options? When it is a missing value.
That's what we have. 0, we have mean, we have different things. So next is the mean value. So first we need to calculate the mean value from the data set. So we'll go through the data set. So select expression will take the expression on the data set. So we say mean of that specific column, and we just say first off get double. So we'll get the mean value. Then we'll use the same similar method which replaces those missing values with the mean value. And one more option is drop rows. Like let's say if you have like a lot of nulls, so you can say I don't want to consider that, I just want to drop the rows. So you can drop. And if there is any other value, like let's say if it is a string value and it has nulls, and user knows what it should be, kind of user may put like a NA or some kind of default value which user knows. So that is also supported. We can just take that specific value and then we can replace it.
Depending upon the context of the problem, without the domain knowledge, we cannot decide on whether to drop it or increase it.
No, that requires. So this will be used by a domain expert actually. So this code will not be written by a domain expert, but that will be used by a domain expert who will have knowledge about which to call. So our task is to provide an API which supports different types of handling. So here we are not making a decision on how do we want to handle. We are just providing different options on how it should be handled. If you see, we have also implemented the transform schema method. So we are not doing any of the logic because our code is capable of handling different data types and different mean and other things. Maybe we can add some more validation that whenever user says he wants to handle with a mean, so then the data type should be a numeric type instead of like calling a mean on a string type. So those kind of validations we can add. So, but basically we don't have a strict requirement on what should be the data type and other things. So that's the reason why we are returning the same schema. So we have other examples of where we will be using that method more, and we will be talking about that. And there is one more method. So normally all of the Spark ML stages have a UID for them. So normally we kind of generate the random UID, so we don't ask it from the user. So that is basically to kind of save the model, and when you get back the model, so to verify whether the model you had before and the model you got now is the same model or not. So here we are kind of generating a random UID. So this method is a kind of a 0 parameter constructor. So if you scroll above, so the class is taking a UID actually. So if user is not providing the UID, then we can override that with this constructor, the zero parameter constructor. So that's about the thing, and there are few copy and other methods. So this is for internal use. So it will, whenever you say the specific null handler dot copy, it will copy all the parameters to the new null handler what you are getting. So it's kind of copy on a case class in Scala. So one thing, yeah.
Quick question. Because we are returning the same schema, are we expecting the value which we are filling in the data?
Yeah,
That
with,
column
with
is
yeah.
already present.
Yeah, so currently we are doing that because actually in Spark when you have nulls in the data, so that schema doesn't change. Like if you have a numeric type and if you have few nulls, the schema will be numeric type itself. So null is a completely different type in
But
Spark.
you are actually even calculating the mean. So mean is not just a null value. In one of the options we are calculating mean also.
Yeah,
Where are you filling the mean?
I'm filling the mean above actually. So you mean where are we filling the mean?
So I'm asking, will that be filled in another column if you are adding this in this transformer?
No, it will be updating the same column.
Present.
It will be like doing an in-place update. So it will be updating the same column name. So we are not taking the column. So next is about like how do you control the configuration. So what is the input column? What is the output column? So there is params. If you just scroll above, so there are like different classes we have implemented. Something called has input call and has handle with. So whenever we kind of support parameters for our ML stage, so we use a params kind of a framework inside Spark to kind of support that. We just go into the has input call. So basically it has a param which is of type string. So we can give a name to a param and kind of a description. So normally this description and name is used whenever we get an error or something, whenever a parameter mismatches. So this will be used, and we can give a method, some kind of a utility method where you say get input column will extract that param from the param map and then give you. So Spark internally stores these things in a param map. So we kind of have this method to kind of get this. So this is a trait. So the idea is that so there are different ML stages what we will be building, and we will be everyone will be expecting an input column. So we will be reusing this parameter in multiple places. So that's why we have it in a kind of a general place where we can reuse that. So and handle with also is similar. It's also a string param, and the code to use it. So if we just scroll towards the end, so we no not this one, null handler transfer. Yeah. So if we just scroll towards the end, so we are creating a Spark session in the first time. So we have like a local and we are giving the app name as example. So we are creating a Spark session, and I have a utility with loads CSV. I think everyone knows like how to load a CSV file into a data frame or data set. So we just give a path and the Spark session. That utility will load the data set for me. So I have the data. So I am printing the number of rows having nulls in the column total bedroom. So it's a housing data set. So it has different features related to a house property. And I am filtering the data is null.
Is the data public available? Like
Yes, yeah. So yeah, I'm checking if the column has is null, and then I'm just counting. So this is to just print like how many nulls are present. And then what I'm doing is I'm creating a null handler transformer, and I am setting input column. If you see, I am null handler dot set input column will take the column name, so which will internally keep that column name in a param map. So I'll talk more about what is this param map, where it is used, and other things. So and also I'm setting the handle width. So I say if the number of bedrooms in a specific property is missing, so I handle with mean. So I don't worry much about it. Then null handler dot transform will take the data and it will handle the nulls. Then after I get the data back, null handle data, I am just calling the same, printing the same function to find out like how many nulls are there in that specific data set. So is the code clear? So similarly, so we have a string column which is a state. So whenever a data is missing in the state column, then I just replace with NA, so that whenever we kind of see that value in terms of label or any places, so we know that it was a missing value which has been handled. So that also we'll kind of do a transform. We'll get a null handle data, and we try to print the number of nulls before and after the transformation. So we'll just run this transformer. So if you see, we had two 207 nulls in the total bedrooms column. So we have like a 0 after null handling, and similarly we had 1000 rows null for the state column. If you see, null is 1099. We did a group by and count, and after we handled, so we got like a NA. So those values were replaced with NA string, so which will be handled gracefully by all the algorithms. So when you see the final output in terms of evaluation or things, the user will be able to differentiate between what NA means. So this is the example. So we'll go to the another main function below that. Yeah. So here what I am doing is, so this is a typical ML way of doing it. So normally when we have a data, so we don't kind of feed the complete data into the train and use the complete data for evaluating or testing or prediction. So basically we divide the data, we do a split of the data into percentage. So normally it's 60, 20, 20. So we divide the data as 60%, 20% and 20%. So 60% will be the trained data, and there will be a 20% test and 20% evaluation kind of a data. So here what I am doing is I am using a random split method in the Spark data frame API. So it takes array of percentage split percentage values. So I give 0.6, 0.6 is equivalent to 60%, 0.2 20%, and 0.2 is 20%. So I have kept the seed because every time it kind of randomly splits. So I want those rows to be going into that specific piece. So I use the first 60% as a test data, and there is another test data I am using it. And there is another test data in which only has columns which has nulls for that specific column. So basically I am using 3 different set of data. In the last data set, all the rows in that has nulls for that total bedrooms column. So there is no like a valid value at all. So now what I am doing is that I am doing a null handler for the train data. I am trying to print it. I am doing a null handler for the test data. I am trying to print the number of rows, and I am doing the null handling for the third set of the data. So we'll just run this. So if you see, the first one was handled correctly. So there were 108 values, rows had nulls, so it was handled. And after that we had 55, and it was handled. But in the third data set, it failed to handle. It threw a null pointer exception. So what may be the reason for that? Which one? Yeah, so in the third data set, all the rows for that specific column had nulls. So now the issue what we are facing is, so normally a null handler, whenever it calculates a mean value, so it shouldn't calculate on that specific data set. So normally when you train a data set, so we should calculate the mean value on the trained set of the data, and then use the same mean value in your test data or the predict data. So we shouldn't calculate the thing on the term. So we'll just go to the slides.
Why should we be using from the train data?
I'll talk about that. So the reason is that, so one is that when you aggregate over the data, so the mean value what you get depend on what are the values, what are the valid values you have in that specific data. When you calculate mean on different data, like you don't calculate it on the trained data, instead when you get the data, you calculate it on the fly. The issue is that, so the aggregation takes time. So normally when you do a prediction, that is a transform is equivalent to a prediction. So when you have a model and when you do a predict, if the aggregations are performed on the predicted data set, it takes time. So normally transformations are meant to be used for row level operations. So you should take a row and you should kind of give back a row. You should not do like aggregations and like going over the data multiple times. And also prediction will be slower. And also normally your prediction accuracy will start depending on what quality of the data in the prediction set. So which is not a right thing actually. So normally your prediction accuracy should depend on the quality of the data in the train set instead of the data in the predict set. So that's what.
That's very strange to hear.
Which one?
My accuracy, if I have to derive everything from the train data, what that means is that I can fit a model which is best suiting the train data, and test data
No,
doesn't match.
let me give another example. You have a linear regression algorithm. So normally you fit train data and you get the coefficients and the intercepts. You use that coefficient and the intercepts for prediction. So here what we are doing is that, so just giving an analogy. So we are training a linear regression on the trained data, and we are again training the linear regression on the test data and using that coefficients and the intercepts for prediction. So which is a wrong way to do it.
See, thing is the concept of training in the test data is this, that you train based on that data, right? And then how you measure that, how good your model is, for that you use the test data.
Yeah, just to answer that question is that here we are doing a null handling, right? So null handling, why we are doing in the mean, I want to see the distribution of the data, and in the distribution, whichever the mean, I want to make sure that all the nulls are near to the mean, so that my distribution always looks like a bell curve. Now what happens is that if you look at the distribution of the data, we have 60% in train, and if you have 20-20 in the test, if I use a mean for each, their distribution will be completely different, because the major data what I have is the train data. I want to use that bell curve to make sure that I take the mean and replace in the test anyway. So what he is alluding to is not to say that you should not use a test for evaluation. You used to use a test for evaluation, but should not use a test distribution to do the null handling, because that is a very skewed distribution, because there is only, so that's what he has made.
So null handling anyways is independent of whether it is a training data or it is a test data.
Not really. So the null handling, what you replace the mean with, should be come from a biggest distribution what you have, and the biggest distribution is the train.
If that is the case, you can take 100%. Why you are doing it 60-40, right?
You should do
That
it on
will be even more
100%
better
if
and
that is
close
the
to your
case.
data.
No, if out of 100%, if you are taking the 60% of the data and if you are learning the model on top of it, the same thing will also apply to the model, right? So why you are not doing in the full data? So that you make sure that the trained data has enough distribution so that it will represent the test and other evaluation data set.
The purpose of dividing the data into 60-40 or whatever proportion is
Yeah.
that because you want to validate whether your model is totally skewed as per your input data or is it valid enough for all the use cases.
Yeah, but here we are just calculating the mean and replacing the mean. So the model is not a distribution. There is a difference. The distribution is not a model. Model is what you are learning, and distribution is where the source comes from.
Exactly.
And it should be same in the test, and it should be same in the train. So if I take a mean of the train, and if I replace, I will take it off. I will take it off.
I don't think.
Okay.
So that's what happens. So normally it should go with like a evaluation, like a fit based model. So where you use the train set to kind of calculate these values and use that calculated value in terms of prediction. So that's where we use a estimator here. So estimator, so here what it does is it takes the train data and it calculates the necessary state which should be used in the transform state. So whenever you want to handle null, if there are mean values, so then you will calculate those mean values. And also if you want to replace in a categorical value, if you want to replace those nulls with a value which has like a highest distribution, so you just take that value and you do all those aggregation type of calculations in the fit part of the null handler, and then you return something called a null handler model. So then null handler model will have a transform, so which will have a similar logic, so which will take a data frame and it will apply the mean or the any other thing, and it will return back a data frame. So when you implement estimator, so you have to implement two things. One is the fit and the transform schema. The transform schema functionality is similar, so it's used for validation or anything. So that you get an error before instead of getting an error when you do a fit, because fit goes over the data and you may get an error like after 1 hour or 2 hours when you are running at scale. But transform schema will return an error immediately, so as soon as the pipeline is called, and we return a null handler model. So null handler model will be a transformer. So then it will have like a transform under transform schema method. So we will go to the null handler estimator to see the code. So yeah, so we have a null handler estimator. We just scroll towards the right. So we extend estimator. Estimator takes the type of the model which will be returned by this specific estimator. So it is called null handler model, so which will be implemented by us, and we take the parameters input column and handle with. And if you see the fit method, so I get the handle width parameter, and I check if it's a mean value. And if it's a mean value, I calculate the mean value and then store it. So now where I am storing, I am creating a null handler estimator model, and in the model I have a param which says set option. So when I say set mean option, so it will take that mean and then calculate it, and copy values of null handler model. Why is it used? Because so null handler model will also have these params input column and handle, because we need to use it there as well. So copy values method given by Spark will copy those parameters into the null handler model as well. So we have the null handler model. If we just scroll down, yeah. So we have a null handler model. So it extends something called model. So it has a model, and if you see it implements has optional mean. So dot set mean value will take an option of double. So if that column is a numeric type, then only we calculate, and if the user has specified mean, so we calculate and then we store it. And in the transform step, the step is simple. So if it is 0, you fill it with 0. If it is mean, you do, and if it's any other value also, you do the same work. But in terms of mean value, previously we were calculating the mean value on the fly. So here we are getting the mean value from the params, so which was calculated at the time of training, and we'll use that mean value to replace the things. So now, since we are not going over the data multiple times in terms of prediction of the transformation, so this shouldn't throw the error what we got in our previous example. So if you see the main function, so I have a same main function, but the only thing is, like, I am using a different null handler. So I am using the null handler estimator what we have right now. So we'll just run this now.
Yeah, there's two questions.
Yeah.
One is, what kind of use case will I be doing this?
In most of the use cases, we should be like handling the nulls, right? So
Handling null is fine, but in which use case will I be calculating mean on test data and copying it to train data?
I think in all the use cases, it should be done in the train set itself. Because let's say you have a predict data set, so which is like a 1 GB or 2 GB file. So now prediction is assumed to be faster, so that you get something and you kind of calculate the thing and you get the output back. So now now when you have like a prediction step doing all these, going over the data, so every time you handle null on a specific column, you go over that 500 GB data and calculate the mean value and replacing it. So that's the first problem. And the next problem is, so what happens if you have all the nulls in that specific column for a test data set? So we will not be able to find a null because all the values are nulls for that specific column. So those are the two issues which doesn't let us use the null handler.
Why do
as
I
a
need
transform.
ML program for this? I can just use the Spark API and do it. Why do I need ML API?
So here we are saying that this null handler goes and sits inside a pipeline. So everything can be done in a normal code. But here we are talking about the abstraction where this null handler sits inside a pipeline as a specific stage. So once we integrate everything, so our complete pipeline will be complete. These null handlers and other Sparks stages will sit together in a pipeline. We just fit a data set and we transform a data set. So that's what we'll be seeing.
Is it a generic, like, you can handle, say for example, with respect to the context of computing Gaggle quality, there are a lot of quality, data that is missing. It's 99% hard effort goes into preparing the data. So the thing is, like, can we develop this written is a generic one, or it is depending upon the data we have to develop some?
It is a generic one. So
it's for the real estate data only.
No, it's nothing to do with the real estate, because we are not like hard coding anything for specific data. So it's a general problem. So there may be few missing features because there is no end to like adding a lot of features. So you can apply a lot of smartness into like handling these data cleanup and other things. So we are not talking about how do you kind of get that perfect product out there. So here we are talking about how do you kind of add those missing features into the Spark pipeline so that you can use it in a better way. So by the end of the talk, I think this will make sense why this is better than just writing like 4 to 5 lines of code of handling a null and then just replacing it in a data frame. Because we have few more things and how the whole thing fits into a Spark pipeline.
Yeah, one thing I'll just add here. I think a lot of people coming here may have a Python scikit-learn experience before. If you go through the scikit-learn documentation, they also kind of talk about the same. Rather than doing a data frame kind of a transformation separately, write a custom estimator yourself for any kind of task. We are taking an example of null handler, but any kind of task, then add it as a pipeline stage. So the nice thing about that is you can reuse across the data set. I think we have an example down in the road, but it is a similar concept. So what we are showing is that how you can do it in Python or other library. Same thing you can now translate it to a Spark ML library.
So mean you had computed on the training data, are you persisting it somewhere?
No, it will be stored in the model. So model can be persisted into a file, so which I'll be talking about later.
Okay.
So
I'm sorry, one more question. So in what kind of situation do you use a mean versus a regular zero or something while replacing nulls?
So normally adding a zero will put off the kind of distribution. So when you use a zero, there will be like, it will be like if you put age 0, then when you kind of calculate mean or like a standard deviations, the whole thing will be kind of put off because there will be a lot of values with 0. So normally mean is to kind of a safe bet so that the actual distribution doesn't get disturbed.
Okay. So null values are typically in a data set are those values where the data is not actually 0 but it is not present.
It's a missing value. Yeah.
It's a missing. So for some reason it is not available. So then let's.
How do you handle that?
Then let's add a mean thing.
That's actually like changes from one problem to another. You can add some problem may solve that by adding a 0. Some problem may solve that by adding a mean value. Some values may be so important that without a valid value we'll not be able to kind of.
So is it a right example that if we say that in an e-commerce data, age of all users is not known because they are not filling in the form or something. So missing values can be replaced by a mean age or something.
So normally it differs. Like how many null values you have, first we need to kind of see. Like if the 90% of the data has nulls for a specific column, then we should typically not consider that column for as a feature in your training. Okay. If you have like a 90% valid values and 10% are nulls, so in terms of age, so we can just take a mean and then replace those values because the 10% will be the users who have done transaction in your thing, because if you just remove those 10% data, then you will be losing out a lot of information from the data. So in that case, you will be replacing with the mean value. So yeah, so next we'll talk about NA values. So here NA values is what happens when the values are not like null. So here null means in terms of like a programmatic term. So if it is not null, maybe for the user it may be null. Even like user may be encoding a null inside a string, or user may be encoding an empty string in place of null, or user may be putting a custom value in place of null. So how do you handle that? So basically we create a transformer, so which will convert all these values into into nulls, and after which if we add our null handler stage, so that will actually kind of handle all these values including the nulls in the data set. So we'll just have a quick look at the NA values handler. So basically it takes an input column on which we want to handle NA values, and it takes a set of NA values, array of string. So where you can say like a string inside, a null inside a string, or an empty string, or a space character, or a double space, or a tab, or anything. So you can encode anything. So basically we have a UDF, so which takes the value of that column and it checks if that NA values are contained, then it returns a null, and it will also check if that value is an empty, that empty string or tab and other things. So then also it will run, it will return a null. In other cases it will return a value, and we are adding that to a specific column where user has set the column name. So whichever user specified column name is there, so we'll just use that UDF to kind of replace those data set. So this is a transformer and not an estimator, because this is a row level operation. For every row we know what are the values we want to replace, and we'll just check if that row has that specific value or not, and then we just replace. So we'll just move fast and we'll just go to the pipeline and see. So next is the cast transformer. So I'll just not go into the code. So it is similar to the NA values handler. So basically cast normally the machine learning expects the data types to be numeric. So whatever the data you feed in to be numeric, and sometimes you may get into an issue where the data is a numeric type, but it is inferred as a string. Basically, it depends on like which source you are reading the data from. Maybe that source is giving a wrong input or something. So in that case, we can use a cache transformer, which will cache the values from a specific type to a double type. So we have an example where we will be using it, and also Spark ML expects the double types in terms of regression labels and other places. So even if it is an integer type or a long type, it will throw an error. So in that case, we can use this stage to kind of convert those data types to a double type, so that we have a smooth flow of training. So we'll just not go into this. We are using this in the next example, so we'll talk about that. So next is, so where all these things fit in. So now we have seen null handler as a set of code, so where we just send a data set, we get back a data set. Similarly with the NA values handler and other things. So now how this whole thing fits into the Spark ML pipeline. So we can also use the custom stages in combination with the built-in stages in the single pipeline. So when you fit the data, it goes through all the different stages and does the fit on all the estimators you have. And when you call transform, so it kind of transform on all the stages you have in your pipeline. So talking about how do we want to handle the categorical versus a continuous column. So in terms of categorical column, we'll be first we'll be doing the NA values handler, then we'll be doing the null handler so that we avoid nulls, and then we'll be doing the string indexer. So we talked about this string indexer, and then the one-hot encoder. So what is this one-hot encoder is? String indexer will index those unique values in a specific column to the indexes. So now one-hot encoder converts this index into a vector. So that, because normally indexes will be like in an increasing number, like 0 to some value. So normally machine learning algorithm thinks that the higher number will be impacting the accuracy and other things. So one-hot encoder converts that into a vector, so that in that vector, so whichever the index you have, so that index will be a 1 value and other indexes will be a 0 value. So that will not have much of a like a numerical continuous effect on the actual data, because this is nothing to do with the continuous number. The indexes were assigned by string indexer. So if we directly use that continuous values will have effect on the actual training. So then we have a vector assembler where we kind of combine all the features what we think, and then the algorithm stage. So algorithm stage is actually specifying the algorithm and then giving all these input to the algorithm. So we'll just go to this example of building pipeline.
Small question. For every transformer, you need to create an estimator.
No, for estimator you need to create a transformer. It's a reverse. Yeah. So yeah, I have a function utility method called create pipeline. So basically what it takes is it takes a schema of the data set. It takes a label column. So it takes only those two things. So by assuming that by seeing the type of the data of each of columns, and it will decide on which different values, which different stages it should handle, and it will create an array of pipeline stages. If you see the return type, it is array of pipeline stages. So pipeline stages is a parent class for estimator, transformer, any of your ML stages. So if you look at the code, so first thing is that we are finding out the columns which we need to create as consider as a features. So here I am just assuming that other than label, everything else should be considered for features. So we kind of do a filter where not equal to label column, we get back everything. Now if the data type is of a string type, so I add few things. So I add NA values handler. So I said this is the field name. I add null handler estimator. So where I said this is the field name, and since this is a string type column, if you see I am setting handle with as NA. Then I add a string indexer. So normally string indexer and one-hot encoder is different than whatever the stages we implemented. It doesn't do an in-place update. Instead, it will add a new column to the actual data set with that indexed values. One-hot encoder will add a new column with the one-hot encoded value, so it doesn't touch the actual actual column what we passed it. So we are creating a string indexer where it says input column is the actual column name, output column is the column name underscore indexed. and we have one hot encoder which will take the indexed column name. So it says input column is column name underscore indexed, and the output column is column name underscore encoded. So now I am adding that final column. So encoded is the feature which we want to use for training. The encoded column is the one which we want to use for training. So I have just a mutable array. So I am just adding it to that mutable array which I will be using it. And I create an array of pipeline stages for this specific column and then pass it. So if you just go to the numeric type, so for numeric type we don't need to do any other things because NA values handler will not be there because numeric Spark forces that type to be numeric. It can be a numeric value or it can be a null value. So we just add handle null and we like a generic thing we use mean to do it. Since we did not change any of the column names here, so we'll add that as a feature column. Then we use all those things. Now if you see below, I'm creating a vector assembler stage. So where it says set input columns. So I take all the columns what I had added to that mutable array and set it as a input columns, and output column will be a features column which will be of type vector. Now going to the actual stage. So we till now we handled only the feature stages. So what we want to do in terms of feature handling. But in terms of label also we need to do some handling because label will be a string value even if you do a like a classification problem. So the label cannot be a like a string value. So
one question is, so this the columns which you are converting to an array and then vector,
yeah,
eventually they can have different types, right?
Which types?
The
No,
type
it can be a numeric or it should be a numeric. So vector assembler expects those types to be numeric type.
Okay, so everything, all the columns have been converted into numeric,
Yeah,
using string indexer or something
string
else.
indexer, one hot encoder. Yeah, all
But
those
all
things
the
are
other
converted.
thing, all of them will be numeric. Then you can convert into an array and then vector.
Yeah, yeah.
Okay.
So in terms of label column also the same thing follows. For label column we will not be doing a one hot encoder because label column cannot be a vector. It should be a actual double value. So we just do a string indexer. And for in terms of the label column is a string type, I create a decision tree classifier. And if it is a numeric type, I create a decision tree regressor. So it's a simple logic which I am using. So again, I am handling nulls for the label column. So we need to handle nulls for the label column as well because Spark ML throws a runtime exception if there are nulls for the label column, and it's hard to say from the error that the error caused was because of the nulls in the label column. So we created that and we return the array of stages. And if we scroll down, now I am combining all of those things: pre-processing stages, the string indexer, null handler, all those things. Then the vector assembler, so which will convert them into a feature, and the algorithm stages. Algorithm stages contains the algorithm and also the pre-processing for the label column. So all these things combined, it will return an array of pipeline stages. So now if we see how we create a pipeline, if you see I wrote a data set using the same utility. I say create pipeline, I give the schema of the data set and I give a distance, what is the label column which I want to consider in this specific use case. Then I say I get the pipeline stages, I say create new pipeline, I set the stages whatever I got, and I say fit of the data. So fit is similar to training. So now the training happens. So I'm just calculating the time what it takes for the training. So now it returned the pipeline model. Now pipeline model dot transform is like a prediction step. So now it goes through all the stages. It takes the data set through all the stages in the pipeline model, and also finally it adds the prediction columns. Like if it is a decision tree classifier, it adds the label column. If it is a decision tree regressor, it adds a predicted column, and it will give the best. So now, since we are able to use that, use the stages in combination with the Spark's built-in stages in a single pipeline. So now the usage is very simple. So here we are not playing with, we are not just creating sending the data to some utility which will handle the nulls and return us, which we are not sending our data to a separate code which will just do something. So everything is encoded in a pipeline stage and it will be used in these terms. So basically the problem what we are trying to solve is, so normally these custom Spark ML stages will not be created by all the user. If let's say in a team, in a company, so not everyone will be creating these custom ML stages. So normally there will be a separate team which will be kind of creating these things which are required for the product, and many people will be consuming it. So the advantage what we get here is you have like a code in a single place, so it is easily maintainable and other things. And also, since many people are using it, so there will be strict APIs and other guidelines which will be maintained by the team. If they are writing their own, so utilities, everyone knows like how people maintain the utilities function. So they just pass whatever they need and they just return whatever they need. But this will not let the things.
So here you have trained and predicted in the same piece of
Same
code.
data set. Yeah.
But this is not a typical production pipeline.
No. No, this is like you can use this pipeline in the production, but it's not like you cannot pass the same train to the train
Like
data
there
set.
are two things. One is that you will train once or populate some granularity, but you might be predicting often.
Yeah. So
And the other thing is that you may not be, you may want to predict on a online basis, like you have
yeah,
a model in
that's what.
online
So,
system.
Go to the code. Sorry. So if you see, this is the train step, the fit method, whatever I am calling. So that is the train step. So that will be run only once. We get a pipeline model. So we will store that pipeline model, and whenever you get data to be predicted, you just call the transform method to kind of get the prediction.
How do you store it? Spark provides the APIs.
Yeah, I'll talk about that. So there is a set of APIs to do that. But we'll store the model and we will use that model to call dot transform. Transform takes a data set, so which needs these columns to be of this schema and other things. So whenever you get a data from a external source, so you just take the data, pass through the transform. So now, since everything is encoded in a pipeline, you don't have to do null handling on the test data separately by sending it to some utility. So everything will be inside a pipeline. So dot transform will take you through all the stages. Like it replaces null values, it replaces NA values. So it handles nulls, everything, and then finally you will have the final thing. So if you see number of stages, so we had a 29 column data set. So this was a 29 column data set, and we created like 65 stages for them. So like the string columns had like I think 4 to 5 stages. So we had algorithm stage, vectors, and that. So totally it had like a 65 stages, and I'm also just printing the time taken for the training step. So is this clear? Any doubts?
Is this
Take a
pipeline?
break now.
Sorry. Okay.
Is this Spark pipeline also available in PySpark?
I think so.
Yeah. So
Getting into that, so we'll discuss about one more thing. So iterative programming in Spark. So Spark is a kind of a iterative programming. So it is one of the big data frameworks, so which has support for iterative programming. So you can go over the data multiple times. So and it has something called lazy evaluation. So which gives better support in terms of iterative programming. So when we go over the data multiple times, so basically what happens is that so you do multiple steps. So individual steps you can store it in the RAM or you can persist somewhere, or those steps are kind of accumulated in a plan. So normally it creates a plan about what all you did on a data set. You have a data set in your file system. So you did like 10 different steps. So Spark keeps track of what are the 10 different steps you did on the data set. Only when you kind of trigger operation like save or doing some calculation or aggregation, so that is when it actually runs all those steps. So basically running those steps requires some analysis of that logical plan, because logical plan will be of a specific structure. So it has to analyze that logical plan, create like Java bytecode, and it should run that in a actual physical system. So it has to run that processing in a physical system. So that's what iterative programming is. So now the issue is that so growing logical plan. So as you do a lot of operations on a specific data set, the logical plan kind of keeps on growing to a different size. So you can solve that problem by caching the data set. Like after a specific set of operations, you can cache a data set. But what if you don't have like so much resource to cache the data set? If you are working with a terabyte of data, you already cached the source data. So now if you want to kind of cache again like this intermediate data, you again need another terabyte of RAM to do that. So which is not a good idea. So normally what happens in ML is that, so this problem is more persistent when you work with data sets which has hundreds of columns. So when you have like 100 column data set and you're doing some processing, so you'll get into this lineage issue where Spark kind of keeps all those 100 columns. Like if you see we had 30 columns and we had like 65-70 stages, and if it is a 100 column it will be like 200-220 stages. So Spark has to keep all of those things in memory and kind of do the processing in the driver, so which is puts a lot of overhead. So this is basically compute bound because plan analysis is done in the Spark driver. It is not like a distributed work of the executors. So that's one of the issue. So we have an example where when we simulate a data set with 100 columns and run null handler on top of it. So after some time, so the actual running or actual calculating the mean value will take less time compared to the plan analysis. Like if the actual data is I think 1 or 2 MB, so it takes like 10 to 15 milliseconds to calculate, go over the data and do some operation. But to kind of do the plan analysis towards the end, it takes like 1 second, 1.5 seconds. So, and also that keeps on growing as you move towards the end. So that is the issue what we faced. So now how do we solve that? So multi-column handling. So reducing the number of stages in a pipeline is one of the solution to reduce the lineage it grows on. So how do you reduce the number of stages? Because normally stages depends on how many columns do you have and how many things. But internally logical plan is every operation you do on a data frame or a data set, it adds another step to the logical plan. So we should somehow reduce the number of steps. So there we can build pipeline stages which have the ability to kind of do the processing on multiple columns at once. So if you see, we had like 30 null handlers for 30 columns. Instead, why can't we do that in a single null handler? So which is able to accommodate all of those columns and handle null at a single thing. So here we are not talking about any other performance, only reducing the number of steps in the actual iterations. So this improves plan performance drastically, because if you have a 30 column data set, so you reduce the 29 transformations to only 1, so which is a huge number, and that's one of the things. So we will go to the multi-column null handler. So I'll just show you like how that is done. So if you see, previously we were taking an input column and handle with. Now I take a map. So map key would be an input column and value would be how do I want to handle it. So again, it's an estimator. So in the fit, if you see, I go through the handle map and find out the list of columns which has mean handle with. So I calculate their mean and create something called a mean value map. So mean value map would be a column name and a double as a value. The mean value will be stored that, and the multi-column null handler model, just scroll down. So multi-column null handler, it takes a map of string double. So this string double will contain the mean values for that columns which user had specified to be handled by mean. So now you have both the things in the thing. So we cannot use that data frame in a functions anymore, because that always like handles with a single column. And also there are like few disadvantages. We cannot use that here because there is only, it takes one column and updates that in place and it returns back. So basically we kind of write the expressions to handle nulls. So callsec is one of the expression which is used. So basically what callsec does is, so callsec takes two parameters. So one is the column value. So here, so this is how you create an expression in a data frame way. So I say this is the column value, and if this is null, so what callsec does is it takes the second parameter and replaces it into that specific value. So the second parameter is a mean value, and I'm casting that mean value to whatever the column type is. Like if the mean value will be double, so column type, if it is an integer, so I just cast it to integer and use it. And also I am handling 0 also here. If you see, I try to get the mean value from the map I had. If I don't get the mean value, I just fall back to 0. So here 0 means I can kind of handle both here. And also if it is a double or float, I am casting that. I think that means. So I am just handling the mean, and if there is any other handle with which is of type numeric type, I cast to the column type, and whatever the value user had specified, I convert it to double. Like if user had specified the values in string, because we are taking handle with as string, right? So if the string value is, if user says put the value, default value as 39.0. So now we need to convert that to double because the column type is of double. So that's what I am doing here. And if it is not a numeric type, I just put the string itself as it is. And now only feature missing is the drop rows. So now all these things will be expressions to handle null. Dataframe.select will give you the will handle nulls on all the columns in a single expression. So this will add only one step to your logical plan. It will not add like a 30 steps to your logical plan. So this is one of the way. And also, if you want to handle drop rows here, so we may have to add an additional filter, which will add another step to the data frame. But there is no like other way to kind of do it. So we'll be using max 2 steps to kind of do the null handling on any number of columns you have. Is this clear?
Question.
Yeah.
In this case, how are you differentiating between features which is category value continuous?
So here we are not doing that. We are always going by the type and whatever the handle with user has specified. So here we don't have the logic about whether it's a categorical and numerical. So here we are not treating a column as categorical and numerical. So here we go by the data type or whatever the user specified information. What user says if you want to handle with theme. So that will be done at a separate. So we have an example to kind of use that. So the growing lineage issue, whatever I had an example before, if we run that example, it takes around like 22 seconds to kind of run this run null handling on 200 columns, which is the old null handling what I've created. So whatever we have created now, it like takes 2 to 3 seconds to kind of run the null handling on all the 30 columns because we are going by the on a single row of data and we are not going like multiple times over the data. And another advantage is like there's a lot of scheduling delay. So like plan has to be processed and other things. So that delay doesn't exist in this example. So that's the basic difference between them. So just go back to the slides. So the code is completely kind of like it is self-serving. So you can just pull the code and you can just right click and then run. Everything will run without any issues. So it will just download the dependencies and it will run automatically. So next we'll go to the training part of the equation. So we looked into how the data cleanup and how the pre-processing works and what are the missing features. How do you want to do that? And another key takeaway from our that multi-column handling is whenever you write your own custom Spark stage. So make sure you handle like a multi-column support because that is very good in performance. And also there is a Jira for Spark's internal stages like string indexer and other values to also support this multi-column so that it is better performant. But it's not been implemented yet. But there is a Jira which I have referred towards the end of these slides. So which kind of keeps track of what are the Spark's built-in stages people are asking for it to be implemented in a multi-column way. So next is the training piece. So when we come to the training piece, so we'll talk about the data sampling. So normally ML makes like a data-driven prediction by building a mathematical model around the data. So whatever the data you give, so that's what ML knows. ML doesn't know anything else in the real world. So it just depends on the data. So to avoid overfitting the model, normally what we do is like we divide the data into train data, test data, and differentiate. And train data is used for learning, and the test data to verify the model accuracy and how it is performing. So normally data is divided into 2 samples. So as I already showed you, so there is a random split method which takes an array of percentages you want to divide the data into, and it will divide the data. So one of the advantage of this random split over whatever the normal other sampling methods on the data frame is, so it avoids overlapping rows. If a specific row is in the train data, so it will not be there in the test data. So that is very tricky to do in your like terabytes of data, but random split provides that feature. So it will not have like overlapping rows. But there are other sampling strategies on top of data frame like dot sample, so which will not give you a guarantee on the overlapping feature. So that comes at a cost. So now we'll talk about caching the data. So we talk about like how we build the stages and other things. So now whenever we kind of do a fit, if you see null handler does a fit, it goes over the data and calculates the mean value. Now there may be another string indexer which goes over the data, calculate the unique values, and there is an algorithm stage which may go over the data multiple times. So now you're going over the data multiple times. Now what happens is that if you kind of cache the source data which is going into the pipeline, then your processing would be much faster, because since this Spark is lazy, so every time you kind of do a processing, calculate the mean, so it reads the data from the file, does the processing, and then just forgets about the data. Then whenever you do another operation, it again goes to the file to kind of read that, unless you cache it manually. So it's good to cache the source data and kind of then pass that cached data to the pipeline. Then you will have a better performance in terms of machine learning, because machine learning is an iterative processing. There are options to cache it in disk as well. So you can use, if you don't have the luxury of storing it in RAM, so you can always use a disk-based persistence as well, which will store it in the distributed nodes, the executor nodes. It will store the data and it will read from their disk, which will be much faster than going to the source like a MySQL database or a S3 or HDFS or anything. So, and caching data speeds up. So next thing is, what is the best practice to do that when you combine both the things. So sampling and caching the data is necessary in terms of Spark. So one is that for the accuracy purpose, and another is for the performance purpose. So you do the sampling for accuracy and you do the caching for performance. So normally people who are in Spark does both. So they do the sampling and they also cache the data to kind of get the thing. But normally what happens is that normally people cache the source data, then do the sampling, then you get like a train data and the test data. So typically you have the source data in memory, so you have everything in cache. So train data, you fit the model, and the test data you use for evaluation or anything. So one tricky piece is random split. So random split goes over the data and sorts the data in order to avoid overlapping rows. So when it sorts the data, so it identifies the hash key for each of these rows and makes sure that doesn't kind of come in one file or one set of data and another set of data. So there is no overlapping. So in order to do that, so it caches the data. So now even though the source data is cached in the memory, whenever you do a random split after that and then use that in your pipeline, so every time you do some operation, it has to sort the complete data. And everyone knows like the cost of sorting on a large data, how much time it takes, and if you are doing it in an iterative programming manner, so it will be very costly. So we'll just go to the example, we'll not just run that pipeline with sampling. So if you see, I do this, so I create a data frame with 100 columns, I say data.cache, so it caches the data in memory. Then I do a random split, I get the train data and the test data, and I say create pipeline, I fit the train data and I transform the test data. So in this case, every time we kind of go through that, every time a pipeline stage goes through the data, it actually sorts the data. So now the reverse way is, I have commented 2 lines here, so which will cache the train data and the test data, so which should be used instead of caching the source data. So there will be a major difference in the performance when we are working in big data with this small change. So that's one of the things. So we'll just go back to the slides. So next, yeah. So this is the difference between the plan. So this is from the Spark's UI. So when we run a specific job, if you see, this is one of the job plan which was ran. If you see, it did a sort. It did a sort, and then it did a hash aggregate, and then it did a exchange, and it got the mean value. Same way, if you cache the train data, which is already random sampled, so you don't have that sort piece at all. So you remove the complete sort, because the data what you had stored is already sorted. So is already kind of sampled. So you need not sort the data again. So you will get away with the thing. So this will have better performance. And if you see, sorting takes around like a few milliseconds, and compared to other things, sorting is the costliest one. So this was a small data, and if you are working with big data, this can have a big impact on your overall performance. So next is another is that normally if you have like a 200-300 columns in your data set, people do not run machine learning on those 200-300 columns. They may be selecting like 50 or 100 columns. So now one smartness what you can apply here is cache only the required columns for your machine learning. So normally this 1 terabyte data if you have, and if it has 100 columns, if you are training a model with 15 columns, so normally it takes around 15 to 20 to 30% of the actual size to store it in RAM. So it's always good to kind of select those features way before. What are the features you want to select and what is the label column? Just do a select on them and then just cache the.
I have a question if you don't mind. It takes, for example, I have taken the same driver prediction challenge. The data feed is running for up to 10 days now. I developed my own local genetic algorithms. And is there any way that I can smartly select the 15 columns you told out of this 55 columns?
We will talk about that. There are few ways in the machine learning where you can do that, like PCA and others, where you can select the principal components out of combine all those columns and take only few. But we are not covering it in the session. I'll talk to you in the offline. So that's one of the optimization. So which which is a small thing, but it has a big impact when you are working with big data. So you can just cache only the required columns, which will reduce the amount of memory consumed for your thing. So next we'll talk about the Spark caching behavior. So Spark has the memory and the cores for processing. So Spark uses the memory for two things. One is that it caches the data, like whatever the caching till now I was talking about, and also processing needs some memory to kind of load the data and do some calculation and other things. So previously in the older versions of Spark, there was a specific boundary, like 60% will be used for caching and 40% will be used for processing. So normally there was no ability to kind of the cache data to kind of move to this boundary and the processing data to go to the other boundary. So the disadvantage what we had before was, even though if you have like a lot of memory in the processing side, so caching data or caching memory was not able to use that, and even if you have a lot of data which is not cached, and if you have memory left in the caching part, so the processing was not able to use that. So to resolve that, so Spark what they did, they got rid of that specific restrictions. So they use the complete memory. So now when you have a memory, and if you have like a lot of data, if you have like 1 terabyte memory, and if you cache 1 terabyte data, processing does not have memory to kind of do the calculation. So what processing does is, processing keeps on flushing the data to disk, and then so that it frees up some memory for processing, and then whenever again you need the data, so it goes to the memory and the data is not present, and it again goes to the cache to read the thing. Again there is a processing on that data, processing will try to acquire memory, and that will be flushed to disk. So it kind of goes in a repeated loop that it takes a lot of time than expected. So it will be kind of caching the data, and the processing will be removing that, and cacher will be again caching the data, something like that. So it kind of goes on in a repeated loop. So one advantage is that we have a storage level. So when you have like a disk available, when you don't have a RAM available, like such a big RAM when you're working with large data sets, so you cannot, it's always better to kind of manage the memory in such a way that you write to a disk if you don't have memory, so that you at least leave out like 30 to 40% of the memory to processing. So that's the actual good practice. So now you know like the source data, when you cache, what happens. So now there was an issue with the actual algorithm. So it's nothing to do with the source data. So I'll talk about that now. So this is with the tree-based classifiers like random forest, decision tree and other things. So what they were doing is, so they were caching the intermediate data. Like they do a tree processing, and they were storing the tree data in memory, which was around like 3 times of the source data. So if you have like a 20 GB as an input to your decision tree, so it will cache around 60 GB of data in memory. And it has ability to flush to disk, but we see like what is the issue with that. So they were caching, and there was no way to kind of switch off that cache or even control the actual storage level. So you cannot flush to disk. So everything was cached. So in that sense, we faced that issue. So whenever we say that we want to train a decision tree classifier on 20 GB data, the requirement was we need to have like 60 to 80 GB of RAM, so which is completely impractical, because if you go to terabytes, normally we don't have that much amount of RAM available, and also there was no config to disable cache or control the storage level. So what we did was, so we went to the Spark source code, and we were able to give another parameter in the Spark's decision tree and other tree-based classifier param. So where it takes an intermediate storage level in the API itself now, and we will be able to kind of set at what level, because we cannot switch off the caching, because that will have a major impact on the performance of the decision tree algorithm itself. So we don't disable the cache. Instead, we tune the storage level. So now it has the ability to kind of store the disk, store it to disk or any other place. So we have that ability, and the changes have been given in this pull request. So it was created by Madhukar, and these changes may land in like Spark 2.3.0. And now since the changes has not gone into the Spark end, so how do we use that? So this is a link to the. So this is how I use it in SBT. So normally SBT has this dependency management. So I give the dependency that Apache Spark package. So what is the library name? What is the version? And SBT has a way to kind of get the jar from a different place instead of getting it from their repositories. So I say from, and I give a URL to place where I have stored the jar. So the change is what I have done. So I need to build a jar out of it and then store it in some place and then get that jar here. So if you just
you have 3 minutes.
So that's one. So and if you go to the code and the SPT, so we are using that, and also in one of the example we are using the intermediate storage level as well. So we can refer that. So next is in terms of operationalization. So many people were asking about the model persistence, so like how do you persist the model and other things. So all the Spark's ML stages supports persistence out of the box. So there is a method called save on the model, and also model.load, which will load the model from the specified path. So basically what it does is, so it takes the params whatever you have and it writes into a Parquet file underneath, and it reads the params. So that is one of the reasons why I said we need to use the params for all the algorithms like input column and other things. We can also take it as a method or like a class level parameter. Why didn't we take instead we use the Spark's params API to kind of get that? Is because we have like a get free persistence in terms of that. So only work which needs to be done from our side is the stage whatever you create should implement default params writable class. So which will give a default, which will give a implementation to kind of persist that file, and only params will persist it. So other inputs whatever you are taking at a class level or any other way of passing an input to the algorithm will not work here. And persisting the pipeline, when you do a persist on the pipeline, it internally calls persist on all of your stages, so that it will store the whole pipeline as it is. And when you say pipeline.load, it has the ability to go to each of those stages and load individual stages and create a pipeline plan. So we have that support. So yeah. So this is about reading a persistent model. So when you have a custom stage, so how do you support reading? So custom stage requires a companion object to your class. So you can just read about companion objects in Scala. So companion object should implement something called default params readable. So if you implement that, so then your stage will have support for reading the model from a file. So and pipeline model.load will internally call the pipelines thing. So persistent params, like if you are using any other param, so you need to provide API how to encode that into a JSON. So you need to. So that's one thing. So you can look at the code to kind of do that. So next is predict schema check. Whenever you go through predict, so Spark does not have the ability to kind of validate the schema it requires for a pipeline because it throws random runtime error exceptions. So user has to manually check the schema whenever he gets a predict data to kind of validate. Next is feature names extraction. You can look at the code and you will be able to kind of make it. This is a set of references we have. We have a few issues linked to the Jira links and also the documentation link. So this is it in terms of the ML productionizing.